We're good.
So hello everyone, welcome to this live stream. I'm Val from Improbable Matter, of course, and this is the first stream where I've got a guest on, and something that I've been hoping to do for a long time, and especially we've got a really good guest for you with Adam Finley, who's going to talk to us about solar physics. We're going to look at a lot of interesting science, a lot of interesting plasma physics. So yeah, hi Adam, and why don't you tell us about yourself and
Hello. Yes, thank you for having me. I'm Adam. I'm doing currently a postdoctoral researcher in France, in Paris. We can come back to my research institute in a minute. But just to give you some background on myself, so I've been here for the last 3 years, and I've been working on doing models of the sun and the sun's atmosphere. Before this, I did a PhD in the UK in the southwest in Exeter, where I was more focused on astrophysics, and then I did a master and a bachelor's in Lancaster before that. So that's like my academic trajectory to get to here.
so that's yeah, that's pretty good. Hopefully, I know we have a lot of aspiring students, a lot of aspiring scientists. So maybe we can, at the end we can field some questions about that. Let me then ask, how are our audio levels? I think I was just fiddling with them, so if we've got a bit of a delay on, but when people hear me, please tell me, can you hear us, just to make sure, and what are our levels like. Now, so you're at CEA, and you guys do a lot of stuff, not just solar physics, of course. So you guys do a lot of interesting research that I think, quite frankly, some of the fusion startups that I've done a lot of talk about should also maybe bear in mind. So why don't you tell us about the broad research that you do at CEA and that other colleagues of yours do?
Yeah, so I think it's interesting to point out, as you say, that CEA is actually a center for primarily nuclear and energy research for the French government. And the interesting thing for why I work there as an astrophysicist is that when they were developing reactors and developing measuring radiation from sources, in the past they discovered that there were sources coming from outside of the Earth, and these now we know are called cosmic rays, and these are things that are coming from extragalactic sources like collapsing black holes and other things like this. And so they created a smaller division inside of this nuclear research and energy research facility in order to basically measure astrophysical processes and sort of classify them so that they could remove them from the measurements of radiation. And so that kind of has now, in the modern day, spawned into the astrophysics department doing a whole range of things that aren't even related to radiation anymore. The heart of it stays in general around uh, the idea of plasma physics, because obviously we moved from radioactivity towards PhDs where they're both studying the plasmas in tokamaks for the future reactors, and also looking at plasmas in stars, because kind of some of the things are transferable between those two. You talk about different kinds of plasma instabilities, and some plasma instabilities that are obvious for somebody who does a star may not be obvious for somebody who does a fusion reactor. And then more generally, we also have a large group of people who do things like particle physics, so more fundamental physics, so people who are working at CERN. There are people who are working on making the next generation of MRI machines, so magnetic resonance imaging machines, so they can do very, very precise images of the human body and different things like this. So I think we have one of those on our site actually called Neurospin, which is like one of the, I think it's one of the large, the highest strength MRI images in the world at the moment. Um, so it's really quite varied actually across the site. Um, my department itself does a lot of galactic simulation, so star formation, galaxy formation, dark matter, cosmic web kind of things as well. A lot of it is based around like high performance computing. So anything where you would need to do like a big calculation. So if you want to simulate the universe, or you want to simulate a star, or the interaction of a star and its planet, um, my department basically will do a lot of that just because of the computing resources we have as well.
So you've got supercomputers, you've got links to ITER, CERN, very interesting stuff that I'm sure lots of our viewers are interested in. Yeah, okay, so let's talk about the sun. Do you want to kick us off?
Yeah, so I thought just to bounce off talking about CEA, I just mentioned the project that I'm funded by. So the reason why I'm working in France and not in the UK. My boss is one of the principal investigators of a European Research Council grant. So these are big grants that the European community give out to scientists to enable like long-term research projects. So this is a research project that was provisioned to span like 6 years. And this is an interesting project because it's one of the largest projects that the European Research Council can give out. And it basically covers multiple principal investigators over multiple institutions. And the idea being that they want to fund multiple institutes that have different aspects of physics, some physical process, and basically bring their expertise together to make a new thing. So the idea of the project that my supervisor and his collaborators had was, we're really struggling at the moment to make a model of the sun and stars like the sun, where we model the entirety of the sun, because there's so many scales of plasma physics that are going on. So you have the nuclear reaction in the core, you have a radiation problem of getting the actual gamma rays that are produced in the core to then be passed through radiative transfer through the radiative zone. Then we have a convection zone, so we have a huge dynamical convection problem. And then as we go nearer and nearer the atmosphere, the density scale height is dropping really quickly. So it's basically meaning that we're needing to resolve finer and finer scale convection problems up until we get to the very solar surface, where we have very tiny convective cells like plasma, like bubbling at the sun's surface. And then once we go through this layer, we go into the atmosphere of the sun, which is a completely new parameter range of plasma physics, which is basically a magnetically dominated region of plasma physics. And then that goes into the wind. So this idea of having one or a series of models that can connect all of those processes together are kind of the idea behind the project that we're doing. And that involves generating new codes, like building new codes from scratch. So we have computer scientists. So we have basically people who are good at doing simulations of convection, people who are good at doing simulations of the atmosphere, people who are good at making codes, and everyone's working together to do this one problem.
Now, yeah, I got a firstly, I talk about fusion in the lab and hopefully in reactors on my channel. Of course, about 25% of the comments I get are that we already have a working fusion reactor. Why do we need to build a power plant when we have a perfectly well working one? So it's nice to see we are working on that, and it's also cool to see that we have two sort of phases or two regimes where we have the kind of gravitationally confined plasma in the center, but then as you go out, as you said, we've got strong magnetic fields, so we actually have more, let's say, magnetically confined plasma. I think it's fair to say, although.
Yeah, 100%. And one of the other things that the viewers might not know, or they might know very well, is that actually things that happen at the sun also impact us on Earth. So many of the phenomena that happen, explosive phenomena that happen on the sun, like magnetic flares and coronal mass ejections, often have consequences for us on the planet. So we might see an aurora, we might have interference in the ionosphere from energetic particles and X-rays, which might impact, say, for example, astronauts or people who are flying planes or different things like this. And so everything is coupled together in many different ways. So it may seem like spending a lot of money on studying the sun seems like, given the sun is such a seemingly stable object in the sky, seems to be a waste. We should put all this money into studying fusion plasmas and reactors. But actually, the things we learn from the sun can both help us better safeguard our technologies in the future and also develop new technologies like the fusion reactors.
It might surprise you or not surprise you that I've also followed a similar trajectory in my thinking. I did used to think, let's get fusion done, but maybe actually sort of studying the sun is worth it. We can learn a lot of interesting stuff, some of which we'll go over. And again, these techniques that you're using, I think, are very valuable for more people that are working in fusion to try and do. There, in the lab fusion side, also a lot of sort of studying the edge but not the center, or just the center but not the edge. And so that is a real challenge anywhere in any physics simulation where you kind of go across those scales. Yeah. So yeah, that's pretty cool. I have been fiddling with the levels, so hopefully the levels have equalized and so on, and hopefully we've at the moment have a good connection. So yeah, stream-wise. Yeah, so let's, is there anything else you want to say? I mean, maybe just wind it back a little bit. So, there's fusion in the center, radiation's created, it's radiated out, and then it convects out. So is there a reason, or is there a place maybe in the sun where one starts to dominate? Is there an intrinsic swap over there?
Yeah, so basically it's a balance of the timescales for different processes. So in the as the radiation is coming up through the star, the opacity the radiation is facing is changing as a function of distance, and in the radiative zone, it's more efficient for energy to be moved around by radiation, by the interactions, the thermal diffusion of different of the temperature. But at a certain height, temperature starts to build up, and so it allows for bubbles of hot plasma to begin to essentially move out of thermodynamic equilibrium and rise up like you would have in a pan with water. You heat the bottom becomes really, really hot. The water doesn't want to stay at the bottom of the pan, it wants to rise up because it's less dense. And so provided that nothing is taking the heat away from the water at the bottom of the pan, that water will rise up to the top and bubble away and then lose its energy like this. And so we actually see this in other stars that are like the sun. If we add, for example, some more metals, so, and by metals I mean in an astrophysical context, so anything that isn't a hydrogen and a helium, if you add more metals to a star, essentially that all that's doing is it's increasing the kind of opacity that the mixture of plasma in the star is going to have. So that basically triggers this instability for the heat to start building up deeper in the star. And so basically, the stars with the more metals in them that are like the sun have, we think, thicker convective zones. So it's just due to this ability for the temperature, the heat, to be able to move by one of those two processes, and they have two different timescales associated with them. And then obviously once the third transition, I should say again, is once we reach the surface of the sun, which we call the photosphere, then we have all the luminosity of the sun escaping as radiation, because now the plasma has become optically thin and the radiation can just shoot out into space. And so that's what we experience here on Earth when we look at the sun.
So that happens quite rapidly, but I think it's kind of maybe not immediately obvious that it's not like a ball, like a football, where you go from something to almost nothing. There's a lot more of a gentle transition, I think it's fair to say, from the
yeah. So it depends how gentle we're going to speak about.
Yeah.
But definitely there's that extra material. So what I can do is I can show a few more slides.
Yeah, well, let's go through
so
it.
let me just show, just to reiterate, if we think about looking at the sun. So here I'm just showing an image of the sun in like a white light. So this is if you look at the sun with eclipse glasses, so you never look at the sun, but with eclipse glasses, and you had like eyes like a hawk, and you could zoom in. So maybe you can do this with a telescope with a proper filter on. This is just the white light from the sun, but we're like looking at the sun's surface. Essentially, the entire sun's surface is filled with these very small convective granules. So this is the heat rising up and bubbling around, okay, at the very sun's surface. Then we're going to notice that there are some spots, some imperfections in this surface. And this is where strong magnetic fields are on the sun. So this is the interaction of strong magnetic fields on the convection of the sun. So in general, wherever we have a strong magnetic field, it's essentially suppressing the ability of the plasma to convect back up and give its heat to the photosphere there. And so that area will be essentially cooler than the surrounding environment. And we see that as it being dark. But the difference between the actual temperature, so this is the sun's photosphere is 5,800 Kelvin. This is still 4,000 Kelvin. So it's still very, very hot, well, 4,000 degrees Celsius. It's still very hot, but it is much cooler than the other one. And if we shift, I can show you the, if now we're looking at the same images that I was showing you again, with the granular convection that we were looking at. If we shift over to now looking at a magnetic field, an image of the magnetic field, so this is where we've used polarized light to identify if the magnetic field is pointing inward or outward of the sun. So if you consider we're looking at like a north-south bar magnet, or like a magnet you might put in the fridge or play with in school. Then we have the red being the south and the blue being the north. And we'd have magnetic field lines that basically go between those two things. But so this is then showing you, we have the spots on the sun, which is where the strong magnetic fields are suppressing the convection. These are the magnetic fields, and we can see them quite clearly when we make images of the magnetic field.
So maybe worth just saying, because it's a very clever technique, right? If you hold a bar magnet, as you say, from your fridge, it's not going to change. It's not going to affect the light. The light's going to go straight through the magnetic field that's created. But it's with the plasma that when there is a plasma there, and of course it's then being partially confined, partially affected, it's then that the polarization changes. It's very kind of a clever technique there.
Yeah. So here, what we're having actually is iron atoms that have got a few electrons missing are essentially, sitting at the photosphere here. And whenever there's a magnetic field, essentially the light, the levels of radiation that atmosphere, the atom can release are being split because it's sensitive to the magnetic field. And so it's this splitting that you see in the spectral lines. So if you were to use a prism and divide the lines up into blue and red, the splitting of an iron line then gives you the strength of the magnetic field. And then you can also find the polarization of those lines too, to give you extra information, like the angle of the magnetic field.
So it's effectively
it's all very clever. And actually, for the sun, we can do this in quite great detail. We have only a couple of problems. One being that we have, in general, only one observer. And if you're trying to measure, polarization, and you need to know about the angle, actually, the problem is quite degenerate, because you can have an angle away from the line of sight that actually can have quite a few different phases. And so you need two observers to basically identify which way the magnetic field is pointing. But we do use the exact same techniques to try and measure magnetic fields on other stars as well. And so, yeah, it's very interesting. We learn this technique for the sun, and then we try and apply it to other stars.
Yeah, so it's the magnetic field is changing the light, the atoms that are emitting the light, I guess is the headline there. But yeah, and of
yeah,
course,
exactly.
we only have, I mean, the observer though is typically in space still for these kind of observations, but it's typically in space, orbiting specifically the Earth, and so we do only get one view, unfortunately, for most of the time.
Yeah, well, at the end of the session, I can talk a little bit about this, because this picture we have is changing a bit now, with new modern spacecraft. The last thing I'll show on this, just to give everyone an idea. So this is the exact same day that I was showing the sunspots and the magnetic field on the sun. But now what we've done is I've swapped to looking at images in extreme ultraviolet radiation, and I'm showing the different ionized elements here. So this is a helium line, and these are ion lines. And we can see essentially where we had the very strong magnetic fields, we're also seeing a lot of heating, so a lot of emission in extreme ultraviolet. And we can see, like we were talking about the bar magnet, we can start to see plasma that's confined in magnetically dominated loops that basically trace out these bar magnet kind of shape, north-south shapes.
And it's, yeah, I mean, this is, again, real magnetic confinement of plasma. None of this wishy-washy a second at a
Yeah,
time
yeah.
in our labs. This is happening all the time, and that is really magnetically confined, not just by the gravity of the sun. Yeah, and so maybe it's worth just saying, of course, these are false color images because you could not see, you could not kind of with your eyes see 171 angstroms, for example, but they try and color them. Obviously, a very nice sort of color scale. Yeah.
Yeah, and so the one of the ones that's interesting to look at is going back to your point about the sun not being a a perfect sphere, as you might say, in terms of this transition between the different layers we have of like radiative zone, convective zone, photosphere, etc. The photosphere is quite flat as a structure. But we have on top of this, as the material is as the material is cooling, we have a layer called the chromosphere, which is essentially a layer where we have a mixture of many different non-ideal, so we'd say not fully ionized plasma processes that are going on. So we have some neutrals, we have fully ionized bits of plasma, and so we have things like if you might be able to see, it might be hard on your screen to see, but this what we call the filament or prominence. And so this is where plasma from the sun is heated up and condensed at basically sitting on top of a closed magnetic field arcade. So the magnetic field is kind of acting like a bridge, and the plasma has kind of like been heated. It's been sent up the bridge, and then it's radiated all its energy away, and it's condensed down. And so now it's kind of sitting on top of these magnetic field lines. And at some point, it can either drain back down to the sun's surface, or it can explode off into interplanetary space. And so this particular line, which is around 4,000 Kelvin, and then it heats back up again to around 10,000 Kelvin because we have a lot of magnetic fields dumping their energy into the plasma here and heating the plasma. But the more interesting thing is that if we go slightly above this, we move into these wavelengths here, which are actually millions of Kelvin, so millions of degrees Celsius. And this was a problem for a very long time in solar physics, and it still remains one of the things we're doing a lot of research on, which is the heating of this extended atmosphere, which we call the corona. So it's called the coronal heating problem. And the idea basically was, if you imagine our understanding of heat and energy, if I'm stood next to like a bonfire, if I walk towards the bonfire, I'm going to get hotter. And if I walk away from the bonfire, I should be getting cooler because the energy is being dispersed over a bigger and bigger area. With the sun, if you found yourself at the photosphere and you started walking backwards away from the sun or floating back in your spacesuit, it would start getting colder and colder and colder until the temperature increased by orders of magnitude as you were moving away. So you actually want to go back towards the sun in order to be cooler. And so this is a very interesting problem because how is this happening basically?
So it's
And
just a kind of very broad strokes. In the middle, it's about 20 million. Let's do Celsius, whatever it is in Fahrenheit for the Americans. Goes down. The roughly minimum is maybe 5,000, which is right at that surface. The surface of that sphere that you're seeing. You go further out, and it's maybe a few million again, right? And then again,
exactly
at the Earth, it's back down to effectively zero. So an interesting problem.
exactly.
And the other
in general, go
on. So the other interesting thing, possibly that you mentioned there is that we sort of think of a plasma, right? That's an ionized gas. You'd think, okay, so if it's hydrogen, it'd be ionized into a proton and an electron. But as you say, it's actually a mix. There are some hydrogens existing. Even I think some
Yep.
tiny fraction manage to form molecules. Of course, being in a molecule is slightly different to being just one atom, but still there are atoms with just proton and electron. There are free atoms, free electrons, and then there are even some small tiny amount of even molecules that have managed to form. So that's also quite interesting. It's not quite as easy as we maybe think of. You may think you know a plasma, but it's
Yeah,
actually
and as a very tangential point, that it might be interesting for you, uh, is that so people right now when they're looking for like exoplanets around other stars, they're opting to study smaller and smaller stars because it's much easier to detect the transit of a small planet around a small star because it has a bigger effect on the overall brightness. So if you go down to like an M dwarf star, so a star that's like a third the size of the sun, or even like a tenth the size of the sun, and that's about the size of the TRAPPIST system, the star that's in the TRAPPIST system. Um, you actually can have spots. So again, magnetic features on the surface of the star where it's cool enough that you can form water. So you can get actual H2O that's like bonded together, and it's
Mhm.
sitting inside a spot. And so when they're trying to detect, for example, water on a rocky body that's going across the front of the star, they have to disambiguate if it's
Mm.
water that's coming from a spot on the star or water that's coming from the actual planet, which
I
is an
think
interesting problem, you know?
people do find that interesting. I mean, there's discussions. I know that people watch other channels where they talk about, what if an alien civilization put a bunch of uranium into a star to kind of signal to us that, hey,
Yeah.
we're here. There's strange things enough happening as it is, right? So even water, uh, actual molecular water around stars, and yeah, cool.
Yeah. So, and I can show. So if we go back to the heating, um, so maybe I'll just show. This is now focusing on this million degree Kelvin plasma. So we're using one of the wavelengths that's sensitive to that. And we were talking about confinement. This, I think, is a really good example of
Yep.
confinement. You have these, we have, let's say, a positive, source of magnetic field here and a negative one here. So we're making this nice potential field arcade that's going over the top of the two. And you can see if we trace magnetic field lines, from one source to the other, that the plasma that's heated on a field line will stay on that field line and fill that loop. And if we just go to a neighboring area where it's not being heated, it's completely shut off. It's completely cool. And so you can have this very sharp discontinuity between one loop is super hot plasma and one loop is void of plasma, essentially. And if you think from a computational physics standpoint, that is a really difficult thing to model if you're considering you want to model, for example, the entire sun or like the impact of that coming out to impact the Earth. Um, Having actual this kind of like very narrow features, it's not something we normally even include in models at the moment because we
Mhm.
are not do not have the sophisticated enough machinery to do that. You can also see here, kind of the inverse thing of the loop here, is that in this image, it's on the edge of the sun, and I'm trying to show like the void between one loop that's very hot here on the outside and one loop that's very hot here on this side, and then this gap here where we have basically this closed field structure that has not received any heating inside of it.
Another thing, of
Um,
course, is you probably have to at some point look at sort of things like turbulence between all this, right? Turbulence at the
yeah.
anywhere where you get an interface, as we know, it will become turbulent and crazy and unstable and all that sort of stuff. So lots of rich, interesting uh,
Yeah.
science going on there, really.
And so, yeah, the last bit of introductory material that I'd put in here is to mention this process. I'm not sure how much I'll mention it in the rest of the talk, but it's very important for solar physics, which is magnetic reconnection. And this is essentially the reconfiguration of the magnetic field structure. So I've been talking about those loops as if they're like a permanent feature, but constantly the sun is evolving its magnetic field. It's changing through different ways, and one of the ways that it's changing the field is if it can essentially cancel some of the field. So you can imagine one loop with a polarity that's going north-south, another one that's going south-north, and they approach each other. And if you sum them together, you get essentially a zero. And the field can essentially then reconfigure itself into a couple of different loops that then separate and try and relieve the stress, essentially. And so here, what I've got on the left is a video of a very high resolution video of the sun's north pole. And you might be able to see some very small brightenings over the very pole, where essentially the magnetic field is reconnecting and making a jet of material that's released. And a more classical example on the right, which is a very large field structure. So we have a big closed loop here. We have magnetic field that's essentially bubbling up from underneath the sun's surface. It's interacting with this loop, canceling some of it out. And then the ultimate end of this is that it's releasing all the energy that's in the magnetic field into particles and radiation. And these are what we call solar flares or X-ray flares. And you can see it completely in this extreme ultraviolet image whites out the camera. So that it's saturating the detector. It's a very energetic event.
So I think it might be worth kind of speaking about this. I mean, I've done some, not to toot my own home, I've done a little bit of research on this as well. But so the point is, of course, you know, if you had a perfectly stable and perfectly static in time magnetic field, or in fact, you know, it doesn't even have to be static, it could be a little bit dynamic, but, you know, you could basically confine plasma for maybe not indefinitely, but for a long time. You could have one of these loops in principle be quite stable, and you know, it would sit there and it would drag the plasma around with it. The sun actually spins. I guess that's the other thing we should maybe mention, is that the reason we're seeing it, you know, we're seeing it spin relative to the Earth. We're spinning around it, but not quite, you know, we're orbiting around it, but not quite as quickly. So a lot of kind of orbital dynamics going on there. But yeah, so if nothing were happening, you could perfectly well have these loops sit stably. But as we know, and this is why, of course, you know, this is why we can't get fusion really in the lab or in the reactor, is because plasma very unstable, and it's kind of instabilities, and it's the magnetic field being perturbed and the plasma being perturbed that causes these kind of, you know, what you're seeing there, that flare. But likewise, the micro scale, or the, you know, the mini scale little polar jets there going on. It's that the magnetic field being disturbed is what's causing that. That, of course, partially from convection, I think it's fair to say. There's other other forces and, you know, other phenomena going on there. But yeah, and the image on the right there should be familiar to many a lab plasma physicist as well, because that is what their experiments will often look like. You know, if you have a disruption or something like that, it's going to kind of all explode, and the plasma is going to go everywhere. In the case of this, it's going to hit the Earth. In the case of an experiment, it's going to hit your walls, your diverter, and so on.
Yes,
so yeah, very interesting phenomena.
Yeah. I actually lied when I said I had no more introductory things. I have one more introductory thing which might be helpful to people, which is also we haven't really mentioned that the sun itself has a cycle of activity. So I've shown you these images of the sun with spots and, you know, magnetic activity happening on it. But actually, the sun basically waxes and wanes through periods of very low to no activity, which we call solar minima, and then times of very high elevated activity. And in general, this is a cycle of 11 years. And so what I'm plotting here is it's a graph of the number of these black spots that we see in the white light image versus time. And it's going back to when I was born in 1994, not for any particular reason, but that's what I chose. And you can see essentially one sunspot cycle here. So we have a minimum, we go up to a maximum. This is quite a large sunspot cycle by modern times, and a minimum, then to a maximum, but of a relatively weak cycle. So this is the last solar cycle that we had, which had its maximum in 2014, 2015. And then the current cycle, and you can see, as if by chance, was currently discussing it right now. We're currently sitting in the maximum of activity of this current cycle. So the minimum was in 2020. Currently, we're sitting on the axis that I've plotted in this graph. Our grey line is just at the edge of the scale, so we're all the way up here. And what we often do, because the cycle, the emergence of spots on the sun is quite kind of a little bit stochastic and a bit with some biases because we can't see the entire sun and things like this. What we do is we plot a monthly smooth value to compare different cycles with, and then we remove these the month-to-month variation in the actual sunspot to see the actual trend. And so if we do that for the current cycle, that's the red line here. And we take the last two cycles and we plot them on top, we can see that this current cycle is really sitting at the moment in between the two last cycles, which is interesting. And the other interesting thing is that we might notice that we have essentially like a double peak to most cycles. This is quite a common feature. And we would say potentially this the peak in 2023 was the first peak, and then we're going into the second peak now. But if you look at the height of the second peak compared to the first peak, it's quite clear that this cycle is probably going to be very asymmetric in terms of these two peaks. Whereas if you look at cycle 20, this very large cycle over here, the peaks were very symmetric. Here we have an asymmetry. This one's probably going to be asymmetric as well. So it means that we're not out of the woods yet. We still got to have probably a nice burst of activity here before we drop back down.
It's a good thing for aurora watchers because
Exactly, yeah. If you want to see an aurora like people did in May, we've still got a good chance. Although right now we're coming down. So we've just been at a bit of a peak. This month we're coming down, so we're probably back to around where the top of this orange line is. If you want to see just quickly what that does to the sun's magnetic field, if we make a map of the sun's magnetic field, so this is latitude versus longitude, like we've been looking at the map of the world. During a minimum, we have a map that looks kind of like this. It's kind of boring. We don't really have many spots or magnetic features on the sun. We just have a nice, essentially dipolar magnetic field like the Earth's magnetic field, with a northern polarity and a southern polarity. And if you look at the field lines that we might draw from that, it looks very much like a dipole. If I show you so this was at the end of 2019. That's when I was saying the minimum was in 2020. If I now show you the same map that we've made, but from this last month, you can see drastic difference between the two, how much magnetic activity there is, how weak the polar magnetic fields have now become, and how complicated the shape of the sun's magnetic field has become. And this makes a big difference for us if we want to predict, for example, space weather. So things that emerge from the sun and come out to us, generally are going to follow these magnetic field lines. And so if we're trying to figure out which magnetic field line is pointed towards us at a given time, solar activity maximum is one of the more complicated times for us to be able to do that.
Yeah, I guess it's worth saying that there's sort of, so that you can follow the magnetic field to get a line, right? And you can effectively sort of trace it back. You can start at the Earth, which is sort of ensconced in the sun's magnetic field. We have our own near us, but eventually, if you go far enough from the Earth, you're dominated by the sun. And so you can sort of start from the Earth and follow one of these sort of long threads, if you like, back to the sun. And it's quite interesting. Of course, you do a lot of that sort of modeling where you follow the magnetic field, and the magnetic field, of course, confines the plasma. So you're following the route that plasma is taking, the solar wind is taking from the Earth back to the sun. Much harder right now, as you're saying, because we've got a very, very messy sun compared to to just 6 years ago or whatever.
Yeah, and I can show another image here just to give people the idea. So this now is a different observational technique we have. So the sun is in the middle here, in the central circle. And what we're doing here is we're using a technique where we block out the light from the sun, and we look at the scattered light that's coming from the essentially the plasma that's blowing away from the sun, which we call the solar wind. And so essentially that's giving us an impression of like the actual material that's leaving the sun, or the density of the material that's leaving the sun. It's very similar to what happens during a total solar eclipse. So if anyone's been lucky enough to see a total solar eclipse, it's essentially the same thing where something blocks the principal source of light, the sun, and you see essentially the scattering of light from the corona, and you see this kind of structure. And so on the left here, I've got this technique looking at this the sun during solar minimum. So as I said, we had like a dipolar field. So you can imagine field lines that are coming out of the north and south pole, and then closed fields over the equator, and that's giving us these what we'd call like a streamer or a helmet streamer kind of structure. So we have higher densities going around the closed fields. And then if we move to a more active phase of the sun's life, where we have these spots that are appearing on the sun's disk, it's completely changing the structure of the plasma that's escaping from the wind, and we can see we're having streamers at different latitudes. And it's basically making the environment around the sun a more complicated place to model. So you can just imagine modeling this nice simple dipole. Okay, we've got it. Modeling this. Okay, there's a lot of foreground, background, new magnetic features bubbling up, like this kind of thing. Um,
So yeah, firstly, let me just say to anyone, people saying hello in chat, hello, and we do have a question, and maybe we can sort of
yeah, go for it.
answer a simple one and then kind of zoom out. So, with having solar cycles, with having cycles of sunspots, what does that really do to, for example, the light given off by the sun? What does that do to, you know, any other sort of how does that imprint on us, and also I guess to an extent how would that change for other stars?
Yeah, so actually the presence of spots on the sun, so those dark patches, does slightly change the what we call the total solar irradiance, so the amount of energy that comes away from the sun and arrives at Earth. But it changes it so minutely that there's not really any noticeable change on Earth in terms of like modeling for the climate or different things like this. Um, the main thing that is changing during the solar cycle is the various degrees of ionization we have in our atmosphere and in our magnetic bubble. So the area around our planet, essentially, which contains plasma that's dominated by the Earth's magnetic field. So you can imagine the Earth's magnetic field also exerts a control over plasma in its vicinity, and so we have a magnetic bubble around us. But you can imagine having different amounts of irradiation from the sun and different solar wind conditions is changing the kind of plasma environment we have around the Earth. So, for example, and yeah, so the long and short really is the biggest impact that the sunspot cycle has for us is in modulating disruptions to telecommunication networks and different things that rely on the stability of the ionosphere, for example. So if you're making communications from a satellite to ground and you have to go through the ionosphere, it'd be good if that layer wasn't changing like thickness or like its separation in altitude and different things like this.
So that's
Yeah.
okay. That's already interesting. But there, I have heard something. This kind of blew my mind. So we looked at some solar flares there and that sort of thing, and you can see how obviously when the activity is higher, there'll be more flares. But I sort of heard a talk that the sun is quite atypical because you seem to do or you're clued into to the exoplanets and exo stars,
Hmm.
obviously all the galactic neighborhood and that sort of thing. And the sun seems to be quite atypical in the flares, as I understand it, because there's you can watch this on a different channel, but there's certainly discussions of things like, what implications does that have for, say, life on other stars or other planets around other stars, if there's one that is much heavier in terms of flares, or one that has,
Yes.
yeah.
Yeah, no. Yeah, I would say it with regards to the sun being atypical, um, I think the jury is out on that
Okay.
because we lack we lack strong enough constraints on these kind of stars. Basically, we don't have enough stars that are like the sun to do good statistics.
Mm-hmm.
So, for example, if we're looking for a star that has the same mass as the sun, radius, rotation rate, age, and amount of metals, then even by opening up our like acceptable parameters on these things, we're still only looking at like maybe it depends what your acceptable parameters are, but like people who are doing very strict studies are only looking at like 100 stars. And if you think in terms of like if you think in terms of um, things that happen on the sun, like the things that are different things that are changing, so like the sunspot cycle or even longer term processes that are changing. Astrophysics basically works by, we can't look at the sun for, we should really, to know what's going on with the sun, we should look at it for 100 million years. And that is like one good time unit for the sun to be averaged over. We can only look at it for 10 years. So what we should really do is we should look at 1 million stars for 10 years to build a good statistic of what the sun, like how average the sun is. And in most other fields of astrophysics, that's what we do. So with Gaia, for example, we look at as many stars as we can do. We look at them for as long as we can, and then we build up huge statistics so we know exactly what's going on. Um, for if we only have like a few hundred stars that are kind of like the sun, then we can only look at them. Let's say we look at them for 10 years each. We're nowhere near hitting this target of knowing if something's weird or not. But I will say like there are lots of things that people have pointed out about the sun that do make us think that it might be in a bit of a weird phase of its life. So basically, the sun, stars like the sun, essentially, they're born, they have a lot of angular momentum, so they're spinning very quickly. And because they're spinning quickly, they're very efficient at generating magnetic fields. And the magnetic fields are making all the activity and everything and driving mass loss and things like this. And so during a star's life, like the sun, essentially the magnetic field and the loss of material in the wind will basically slow down the star's rotation. And as they age, basically stars, they're rotating fast and then they slow down and slow down and slow down and slow down. And because the process of generating magnetic fields is related to the rotation, there's a feedback loop. And so a fast star will spin itself down, so it will slow down quicker than a slower rotating star. And so at some point in their lives, they basically reach a sequence, like a kind of like a Hertzsprung, you could imagine sequence where they're going rotation versus age, and they all lie on a nice little line. Um, and around the sun's age, stars basically seem to stop lying on this line anymore. They seem to deviate away. And we don't really know why that is. It might be an observational bias because we don't have enough stars, or it might be a genuine thing that once stars get to around the age of the sun, there's kind of like a weakening of the coupling between how it's generating its magnetic field and its rotation, and then they have an onward effect. So some people talk about essentially if we're looking at the sun having a solar cycle of activity, you could imagine at some point its activity drops below a critical threshold for it to maintain activity. And then it would go into like a flat activity. So it would stop having cycles. And one of those, there's a very famous example that people use all the time, which is called the Maunder minimum, which is a long dip in activity that the sun had a few hundred years ago. Uh, and during that dip, essentially, the sun was just basically not really doing its cycle. It didn't visibly do its cycle as we've seen it in other times. And so people use this as a way of saying like the sun is basically kind of sputtering out of activity, right? It's going through a minimum that it can't get itself out of. then it manages to restart, and now it's having a good cycle. And we might go into another phase where it goes into a minimum again, and then it restarts its cycle. But it's like an engine that's like losing its 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 power, and at some point it will go into a very steady state of not really doing anything extraordinary, which isn't bad necessarily bad for us. Um, but it is interesting that we might be catching the sun at this time.
Very interesting. Yeah, I wonder again the implications to other stars. You know, life, what life might be like, because we do like to think about, at least, you know, in principle, what if we went to another star someday? You know, what is it going to be like? There's a lot of stuff you know you might not think. You might think you get there, you know, you set up a colony or something, but there's a lot of subtleties there. I think a lot of you know,
Yeah,
missed.
I think the one of the interesting things in terms of if you want to go to a star that's a star like our sun is knowing better the distribution of large events, like large explosive events that a star can do. So you can imagine that, we have seen in recorded human history a few very, very large um, solar flares slash coronal mass ejections that have driven very strong aurora, like written down the records of having very strong aurora. But at times when we didn't really have a technologically uh, dependent society, right? So that's kind of like a real worry for us right now. If we have like a very big event right now, that could quite possibly damage our network. So we want to protect ourselves. But the way we protect ourselves is knowing what the likelihood of those big events are. So a lot of people are doing a lot of like statistical studies to say, okay, how big is the next big, really big event going to be? Is it like every 1,000 years we're going to have a very, very strong event, or is it like there's a maximum threshold for how big an event is, and we've seen the biggest event. And so now, as long as we can, guard ourselves against the biggest one we've seen, there's no other events. But you can imagine there's like I forget what there's a term that people are using in the literature for this. But it's basically you have one distribution of, we have a distribution for like flare energies of the frequency versus the energy. But if we have some other unknown process that operates at very, very low frequency, like it's 1 in a million years kind of thing, and it's not necessarily directly related to the flare process of just a building up of tension in magnetic field lines. It's something more innate to solar eruptions. Then that's the thing you want to be able to know, and especially know for other stars, because you might send colonists to a star, and then it turns out that actually every 100 years it has one of these massive flares that completely destroys the communication network. And that you'll only know by studying enough stars.
Yeah. So putting on the groundwork early. That's a
Yeah, and so actually, there's a nice mission that's being launched by the European Space Agency in 2 years, which is called the Plato mission. Which the whole point of this mission is to basically look at as many stars as possible and essentially characterize the star and the planets that orbit the star at the same time. So it's kind of like I would say it's a bit of a mixture between like Gaia, which was a mission to map star locations, and Kepler, which was a mission to do photometry. So it's like a bigger version of this Kepler mission that discovered lots of exoplanets. And so that might be a way that we get the good statistics on magnetic activity.
interesting. Yeah, a lot to think about.
Um, I might, if we've got time, swap to talking because I've talked about some of the problems we have in solar physics, but I might talk about some of the potential solutions we have
Yeah.
with new missions.
Yeah.
So, I was saying before sometimes we have a problem where we only have one observer. So, for example, if we're just using spacecraft that are orbiting Earth, um, the sun essentially rotates on its axis with respect to Earth. So if we remove Earth's orbital motion around the sun, it takes around 27 days for a feature on the sun that we see to rotate around and come back, because the sun's rotation period is faster than our orbital period. Okay. And so it means that if we're trying to make predictions about what, the weather is, the space weather is going to be like for Earth in a few weeks, we kind of need to know what's going on the far side of the sun. And we did have a mission 10 or 15 years ago that was called Stereo, which was multiple satellites that we essentially put around the backside of the sun. So we have the Earth like making a triangle in our orbit. So we have the Earth, the sun, and then the two stereo satellites that were basically behind the sun. And so we could do this kind of monitoring. But we don't have those satellites. One of them is broken, and one of them is now basically orbiting near Earth, so it doesn't really do the same thing anymore. But we have a lot of new missions that are in the solar system right now. So we have one mission which I won't talk about that much, which is called Parker Solar Probe, which is a NASA mission. And so that's a mission where they're just trying to go as close as possible to the sun. So in this diagram that I've got here, so that's one, the sun and the one solar radii. This line is 3 solar radii. The spacecraft is trying to go to 10 solar radii. So in terms of like how close it's going to get just twice times this delimiter here out to this circle. So it's going very close. So that's kind of like a fundamental plasma physics mission. It's just trying to measure the plasma that's there. The other one is a European Space Agency mission, which is called Solar Orbiter. And this one is kind of like we took all of the best remote sensing instruments, so cameras and things like this, along with some really good in situ like things to measure plasma. And we basically put it on an orbit that will take it close to the sun, not as close as this, as Parker Solar Probe, but significantly quite close, like half the distance between the sun and the Earth, and also slightly out of the ecliptic, so it'll be able to look at the poles of the sun. So that's one of the things we've never done, is we've never looked directly down on the poles of the sun. So we've always looked at them from this ecliptic plane. And so during a year, this is a diagram that I made just to show, if we look at the year of 2022, we're looking now from the top down of the solar system. So the sun is the black dot in the middle of this diagram at 0, 0. The Earth is on the left, and I'm going to freeze these 2 points in the diagram. So the Earth and the sun never move in the diagram during the entirety of 2022. And what I'm going to show, this is that stereo mission that I mentioned that is now on the side of the Earth with respect to the sun. So you can see that one is not particularly useful in gaining any more insight at the moment. But if we look at, this is the orbit of Solar Orbiter that I applied here. So January, February, March, April, May.
It might just be worth, unpacking, sort of rewinding a little bit. So, normally you'd think the sun is sitting there, and the Earth, of course, must be going around in a circle. So if we didn't have the sun and the Earth fixed, you'd see the Earth as a circle, you'd see other things that are circles or ellipses. This is what happens.
Everything is a circle or ellipse. Everything should be a circle or ellipse.
This is, of course, what happens when you fix the Earth and the sun. And so now those ellipses that you'd expect from, say, a spacecraft or any object should orbit as an ellipse, that's what begins to happen, these crazy sort of spirals, right?
Yeah, really crazy spirals, but it's just showing you the relative position of the spacecraft with respect to Earth. But you can imagine that in January, the Earth and Solar Orbiter are both moving around the sun just in that configuration. And then in February, they're moving around the sun in that configuration. And in March, that configuration. And all I've done is I've frozen, instead of having that all moving at the same time, I've frozen the position of the Earth and the sun so that they are just completely fixed. And so this is now showing you, at any given point during the year of 2022, where Solar Orbiter is in respect to the position of the Earth and the sun. And so the interesting thing to point out is that during the summer months, so May to September, essentially Solar Orbiter, it makes a dive past the sun on one side with respect to Earth, and then it goes out and it goes to its furthest point from the sun, and at that point it's slowing down because it's at its largest distance, so it kind of does like a little double back in its loop with respect to Earth, and then it goes back down towards the sun and it comes and sits with Earth again, and it does the same thing pretty much every year. The interesting thing being, during this time of the year, we basically have a full map of the sun at any given moment, because we can use data, low latency data from the spacecraft to build an entire picture of the sun all in one go. So we combine these observations together. And I can give you an example of that. So I've got, again, the same orbit configuration picture here, but now I'm just showing you for a given day. So all I've done is I've just taken a given day in 2022, so this is May 5th. We have the Earth looking from this direction, so we're top down again. We have this old stereo satellite, which is here, and we have Solar Orbiter, which is effectively on the far side now of the sun. And these are the respective views in one of those extreme ultraviolet wavelengths that we discussed before. So we have the view from Earth, the view from stereo A, and the view from Solar Orbiter. And for one of the studies, I was interested in a given magnetic feature on the sun, so that's why it's highlighted in white here. And you can see if we take each of these observations and we unfold them onto our map, our latitude versus longitude map, we can now make a full image of the sun during this time period. And because the data is low latency, so that means that the spacecraft regularly sends us raw data back to Earth for us to use. We can use this to make more rapid predictions of activity, and know, for example, if something emerges on the far side of the sun, a very large, strong magnetic field concentration, we can know before it's rotated back around towards Earth that we should be ready for more space weather. Yeah, so that's like where we're at now in terms of like studying the whole sun. The last thing I will say on this, and maybe there are some questions, I don't know, about my explanation, is one of the next generation of missions, which has just been agreed to, is European Space Agency's Vigil mission. And the idea of this mission is that we will place one of these, a satellite, just like one of the ones we're using here, at this fifth Lagrangian point. So it's a stable point around in the Earth-Sun system that essentially sits just off to the side of the sun. And so the idea of that satellite would be that we get an early warning to see things rotating around the sun towards the Earth. And it's pretty much a operational, like a space weather mission rather than a scientific mission. So science will benefit from the mission having the data and being open and available, but the prime goal of that mission is to make space missions safer and make better forecasts for people, industries on Earth.
So you're trying to see things like corruption. Now, where exactly would it go on that map there? So am I right in understanding those spiral lines there? That's that magnetic field lines and a ballistic trajectory.
So this would be your flow of the solar wind. So the solar wind is coming out radially from the sun, but because it's in a rotating frame, we're getting the spirals of magnetic fields. And so if we encounter some solar wind at Earth, we can trace back its magnetic field line all the way back to the sun, and its position where it's emitted from on the sun is now rotated around slightly. So we're more worried, for example, if I look at the image of the sun from Earth's perspective, from Earth, we're often more worried about things that are happening on this side of the sun, because we know that given the spiraling of the magnetic field, this side of the sun is more likely to be connected directly to us at any given time.
Wouldn't that be down on the top left panel there, right? Down.
Like this. Like this. So we're looking this way. We're looking this way, and so the right hand of the panel is the down here.
Okay.
So if I look at that field line, it's probably coming to this side of the sun.
So there's one more dangerous side of the sun for us.
So it's like we basically, if you talk about operational forecasting of space weather, you have basically the side where we're doing monitoring. So this, I would say, here we've got full view of what's going on with our instrumentation, and we're basically monitoring, trying to predict if a structure will go unstable and erupt and release material towards us. And then we have a forecasting side, right, which is we might not be able to see around this area, but we need to know what will be coming into view because that's going to change, for example, how much EV radiation, extreme ultraviolet radiation, is hitting the Earth at any given time, or the chances for having X-ray flares that disrupt the ionosphere, and things like this. So yeah, that would be like how I would kind of summarize our thing. And so the Vigil mission is specifically trying to give us more warning on this side of the sun. So things that we can't see that will rotate into view in the next few days or weeks. And that's quite important for it's like, so let's take an extra large step back. If we think about sending people to the moon and to Mars, they are also affected by space weather. And given that if we send people to Mars, Earth can only see some of the sun at a given time. Actually, there's quite a dangerous point in the transit of a capsule from Earth to Mars, like taking people, where we actually would not be able to forecast currently space weather, because they would be in the black in our like no data zone for too long. And so essentially there's a bit of a push right now to build, from both the scientific community and the operational community, to kind of build a network of satellites that can perform this kind of operation, where we have three that are in a network, or even more, that would basically give us the ability to study the whole sun at the same time in order to make better predictions. But it's just very costly to maintain, and no single group wants to do that.
So maybe, Elon Musk might need to drop you a few, or give you some launch.
It's true. At some point, if he wants to send people to Mars, he's going to have to invest in space weather infrastructure.
Exactly. To look at.
So,
and I guess this calculus then would change with Mars, because now Mars is not there on the Earth, so you'd need to see that you need to do the same thing, but with Mars. So which side at any given time is kind of the left and the right side for that, or for part of the transfer orbit? Yeah,
precisely. Yeah.
Very interesting.
So it becomes much more difficult. And one of the missions also that's been proposed is a mission that basically would, so Solar Orbiter, the one that's on the right here, at the moment is still quite in the plane of the planets. So soon it will do some more gravitational assist maneuvers, where it basically changes its orbit by experiencing the gravitational pull of Venus. And it will basically raise the angle of the inclination of its orbit with respect to the sun, but it will only get out of the ecliptic plane by around 30 degrees. So it's going to look at the poles, but from still a bit of a limited angle. So some mission designs for the future have been basically to try and send a similar kind of mission on a polar orbit, so one that goes across around the poles of the sun. So then we could have one mission that's basically measuring the polar magnetic fields of the sun, which we know are quite an important factor for how the sun's magnetic field works in general. And then we have our missions that are in the ecliptic plane, which are doing more space weather. So you have one mission that's doing kind of a climatology survey, and one mission that's doing like a operational space weather forecasting mission. But again, it's all money.
But yeah, definitely
money's got to come from somewhere.
But definitely worth studying. Yeah, I'd be interested to see, working fusion reactor. But I'd also be interested to see, people walk on Mars and base on the moon and things like that. So we probably, well worth studying this sort of stuff for that as well. Cool.
Yeah. So I don't know if you wanted anything else.
Yeah, let's see what else
I can.
I'm curious to see what else you have. Yeah.
So let me try and link you to let's go to, okay, so I've got this image up on the screen. Okay, and I'm looking at this active region here. There's a reason I'm looking at this active region here, and that's because normally so I'm saying active region, what I mean is strong concentration of magnetic field that's bubbled up to the surface. So that's that blue and red that we saw before. And in general, when we have a magnetic field concentration that bubbles up to the surface, it bubbles up in a given place. It forms a nice, like a north-south polarity, It might do some flares, it might do some other bits of magnetic activity, reconfigure the coronal magnetic field. And then in general, it will do, it will diffuse away by convection ripping it apart and by differential rotation ripping it apart. And so you can kind of see this happening to these kind of regions here. They're kind of losing their brightness and they're sort of just fading away and stuff like this. And that timescale for that to happen is normally either on the order of weeks to months. So weeks to months, the region will basically break apart and decay. The interesting thing in 2022 was that if you looked in this area of the sun, so if we look at the map of the sun, in general, during the entirety of 2022, there was something going on in this specific region, this area of the sun. And so you could call it like a hotspot for magnetic activity. And one of the things, we're trying to model the entire sun, and we're trying to learn like what are like fundamental things that are happening on the sun. So when we have magnetic field bubbling up from the inside, from the convective zone of the sun up to the surface, up to the photosphere and into the corona, is there certain areas on the sun that are more likely to have magnetic field bubbling up than others? So I have a little diagram somewhere, I think, of what I want to explain. Yeah. So you could imagine if we see a place on the sun that has a lot of magnetic flux bubbling up underneath it, it could just be like a random chance. The active regions, they're bubbling up at a certain latitude. So in general, they form at around 30 degrees and it can extend lower towards the equator. But in general, they're forming in the same area on the sun, the same latitude. So it could just be random. You might just have like a random chance of that happening. The other thing is you might have something more fundamental going on inside the sun. So for example, the magnetic field that's being generated inside the sun might have an instability associated with it, which causes some magnetic field to bubble up in one hemisphere on this side and another hemisphere on the other side, kind of like a M equals 1 dipole instability. Yep. You could have something like this diagram that I've proposed here, where you have some magnetic field that bubbles up from the surface, and in doing so, it kind of cleans out a path for more magnetic flux to bubble up after it. And then one of our like favored explanations is, so actually we've talked about how difficult it is to model the actual transition towards the surface of the sun, because you're having finer and finer and finer scales of convection. But this is actually something that the magnetic field also has to deal with itself. As the magnetic field bubbles up, it's experiencing more and more pressure scale heights and granulation. And a lot of numerical simulations, when they try to take a box of convection with the surface, and they want to bubble up a magnetic like field, like a patch of magnetic field, the magnetic field actually can't actually punch its way through unless they do a lot of funny tricks with the magnetic field to make it more powerful. And so one of the things we've been thinking is actually what happens if you have something like this kind of like bubbling up snowplow effect, or an asymmetric dipole mode kind of thing. But the flux gets kind of trapped underneath the solar surface. It can't get all the way up to the solar surface. Mm-hmm. And it sits underneath the surface, and then convection at the surface kind of dredges up the magnetic field, and it does it in like a different bursts. And so you have a reservoir that's sitting there for like 6 months of the year, and it's just being pumped by convection every now and again to bring up new magnetic field.
So it's I mean, taking a longer look, it's kind of it's interesting to talk about dredging up the magnetic field, right? So again, normally we're not talking about dredging up. If you had your fridge magnet, magnetic field is fairly stuck. But here, because you have plasma, and that the plasma is sort of giving that magnetic field kind of some inertia, as it were. It's giving it some sort of being, and so you can dredge up, you can pull up, and you're talking about pulling up plasma that's carrying with it this magnetic field, because the plasma is stuck to the magnetic field, but the magnetic field is then stuck through, as it were, frozen into the plasma. So it's being dredged up.
Precisely,
Very
yeah.
interesting stuff that again you might not expect. You might think you know plasmas, but they can dredge up magnetic field. You can plow it up. Yeah, very interesting.
Yeah, really, astrophysical plasmas are very different kettle of fish
Mm.
in terms of the fact that they can essentially the plasma generates itself a magnetic field, which then allows for this kind of phenomena of like the magnetic field is treated as almost a fluid element
Mm.
in a lot of the way that numericists we think about it that way, where it's like a numerical, like it's a fluid quantity. Of course, we know that it's more complicated than this, but it's generally that's how it's behaving in an astrophysical system just because of the timescales and the physics that's going on. So, um, I've given this kind of like a rough idea
Mm-hmm.
of the formation of a hotspot, let's say, on the sun. Now let's use the capability we have with Earth and solar orbiter. So we have essentially, we can monitor the full sun for long periods of time. So now we can look over the course of a year if there are places on the sun that are more active than other places. Um, and so we have a few different ways of looking at that. One, if we imagine taking our map, let me flick around. So let's imagine we take our map that we've made of EUV emission on the entire sun. And then what we do is we basically, over the course of the year, we just like perform a running average, like we sum all of the maps together and we see if there are places on the sun which are brighter than others on a long time scale. And so here what I've got is a map where I've done exactly this. So um, this is a map that contains data for over a couple of years, where we've added all of the EV data on top of itself.
Mm-hmm.
And you can kind of start to see, so you can see I would say you can see two main things. You can see one that in general, the bright places which are corresponding to where the magnetic field is, and we're getting the EV emission, are sitting on these latitudinal bands. And so this is something that is well known in solar physics, that the magnetic field emerges in these latitudinal bands that during the solar cycle evolve slightly in latitude. So in general, the band starts around 30 degrees and it moves towards the equator. And so we've picked a time where it's roughly around 25 degrees, let's say. And so everything seems consistent. The other thing you'll see, which I've highlighted in these squares, these rectangles, is there are some places during these 3 years that I've summed here, where there are brighter patches, right? And we can do another thing, which is we can look at the location of these explosive flares. So if I make a similar kind of thing where I superimpose all of the flares that have happened during this time period, you can see this area here, and I'm going to focus on this one just because that's the one that I've done the research on. This area has way more flares, especially if just looking at the northern hemisphere. The color coding is just to do with the severity of the flare, but we just look at the numbers for now. But clearly, this area and then roughly this area have a predominance of more flares than the rest of the sun.
So it's not maybe so clear, but these are antipodal then. So basically, you've got effectively, if this were the Earth, this would be like North America is one source, but
Yeah,
then the other one is directly to the bottom
it's
right.
like India.
Yeah, well, right, but
Yeah.
it's through and it's on the other side of in
Yes.
this case the sun.
Yeah,
Right?
yeah. Yeah,
Antipodal.
exactly.
So
Yeah,
that's
and so
very
this is why
interesting. Yeah.
people favor this idea that it's like an instability of, if you're having plasma bubbling up in one hemisphere at one side, um, in the other hemisphere, there's a preference for the magnetic field to bubble up kind of on the opposite side to give itself the most space to have, to access one of the instabilities that it can have.
So and
Um,
is it the fact that you say let's call it the North American cluster that starts and then the other it drives something on the other side to then to have
this we don't know, and this we
okay.
can look at the data to get a data-driven picture of this. But for me, I think the data can sometimes be misleading because if we imagine it as being like a reservoir of flux, a magnetic field underneath the surface, then you could have the instability begin, but have no visible manifestation until you have a dredge up or something like this. If that's the theory you go with, right? So there's like a bit of also, we need to do a bit more of a physical interpretation as well. But in general, like when I was doing this research, I also looked back in the literature for other people who've done these kind of studies. And in general, they also seem to find this kind of pattern where you have 180 degrees of separation in the north and the south hemispheres of these kind of hotspots. And that actually they seem to be a persistent feature on very long time scales. So like if we went and looked at like another solar cycle, and we kind of took these longitudes of regions and we advected them with their local latitudinal differential rotation rate. So the surface of the sun is differentially rotating. This is something we didn't mention before, but essentially the equator moves faster than the poles. So for example, something that's closer to the equator will move to the right of this figure. If I go back to like a map of something more physical like the EV emission, something in the corridor in the middle will move towards the right, and something at the top will move towards the left. And then if we at the same a constant, I would say let's say the mean rotation rate of the sun, you stay fixed in this diagram.
So I mean,
like
basically the top is spinning slower.
Is slower.
And the middle is spinning faster.
Yeah.
What we're doing, of course, is trying to pick one, right? And so we're picking, you're saying the 27 days is the average time for it to rotate. And so if we then, we kind of compensate for a 27-day rotation, we're seeing the top rotate slower, so it's moving, it looks like it's moving leftwards.
Yeah.
To the west, the middle flowing east. So different rotation. And we've got stuff that's we've got seemingly a preference for emergence along this other strange axis. Lots of interesting stuff. Yeah, this is
precisely. So if I'll just go to showing the rotation profile of the sun, because I think it's a good point to mention this. So if we cut the sun open and we look inside the sun, this differential rotation persists throughout the outermost layer, the convective layer of the sun. So the entirety of the equator is moving faster than the place where the active regions were, the magnetic field was bubbling up. So if we think this is the kind of latitude where the magnetic field is bubbling up in those diagrams, the equator is moving faster and the poles are moving slower. And so what I was saying about the hotspots is if you imagine the hotspot is located more towards the red side, then it's going to drift. And over very long timescales, like 10, 20 years, the hotspot can drift around the sun. And so in the next cycle, as long as you track where it should be, it will appear again.
Right.
So some authors have done that kind of analysis.
We've had some questions, and actually this might be a good idea, a good sort of time to start answering them. So
Perfect.
We've had a question about turbulence, which is happening, and how does it impact the fusion reaction. So of course now a lot of this actually does happen in Earth, laboratory-based experiments, fusion experiments. There's also rotation in something like a tokamak, and there's also differential rotation to some extent, zonal flows, that sort of thing. And there, of course, it is well known that turbulence has a bad effect on the actual fusion reaction, which is what's important. You guys are doing a whole sun study, or kind of working towards that. Do you have any kind of feel for how does turbulence affect the fusion reactions happening in the sun?
So in general, the fusion reactions are occurring in the inner 20% or 10% of the sun's radius. And as you can see in this diagram, so I've labeled this the radiative zone. That means that below this dashed line, the plasma is kind of stably stratified. So it's in a hydrostatic equilibrium. And so this is not the fusion reaction in the sun is not my area of expertise, but I can say that in comparison to
Hmm.
the what I would say violent convection and turbulence we have in the sun's outer atmosphere, the radiative zone is much more stable
Hmm.
to plasma flows, and so that's why I would
Yeah.
assume
Yeah. No.
that it was not something that people worry about when they're modeling the reaction in the sun. In the sun, it's you have so much pressure that
Hmm.
it's just those nuclear reactions that's going on. We have some waves. We haven't detected them um, uh, undeniably yet, without question. But there are some waves we think that go on in the radiative zone of the sun, which are gravity waves. So they're like oscillations of the hydrostatic equilibrium that can essentially bounce around inside this cavity, and they might have some kind of effect on the nuclear reaction rates. Probably not a big effect, but we also haven't detected these waves. So
But yeah, that might be, again, as you say, your group is working towards this. There's still a very active, lots of research being done clearly, but that might have some quite profound implications. Why is the sun as it is? What if it were suddenly, or what if theoretically, hypothetically, it were more unstable? I bet perhaps it would be colder. What does that have effect?
yeah, I, actually, an interesting one actually. So it moves that even more out of my expertise. But when you move to studying larger
Mhm.
stars, so stars with twice a solar
Mhm.
mass, the core of the star then becomes convective again. So you have essentially like an onion where
Mm.
you have a convective layer, a radiative layer, and then a very tiny convective layer that's stuck on the sun. So actually, then you do have a convective core. So the nuclear reactions are subject to all of the turbulent churning and stuff like this. I have actually not thought about that at all, how that affects the reactions, but I know
Mm.
a lot of people work on that. And the nice thing about working on that is the more massive a star is, the shorter its lifetime is.
Mm.
And so you're getting better statistics on, for example, if I make a stellar structure model and I calculate how long a star should live, for those kind of stars, they die so quickly that you can get a better statistical picture of, oh, my model's wrong because the star dies longer than, it takes longer for the star to blow up in reality than now. Whereas with the sun, something that lives for like 10 billion
Mm.
years and that are quite hard to see with the instrumentation because they're very dim, it's harder to get a good handle on that kind of thing.
Okay, that's
Um,
very cool and potentially very profound. And another question is, again, I think you kind of had a slide that might touch on this, is about the dynamo effect. So
yeah, yeah.
yeah, you can maybe talk about that.
So, yeah, I think I might not have got a slide exactly matching that in my slide deck. But what I can do is if I just go back
Yeah,
to
yeah.
this one,
Hmm. Hmm.
and we just focus on now the very central diagram. So this is just a cut through of the sun, and I'm showing the differential rotation pattern in the color. So we're remembering that we're going faster at the equator, slower at the pole. And if we imagine the sun's rest, let's say the rest magnetic field is that of a nice dipole magnetic field. So we have magnetic field that comes out of the North Pole into the South Pole.
And
And then it's going to have to close because we have the divergence of the magnetic field can't be zero, so it has to close. And so it's going to close back through the interior of the sun, and so it's going to be inside the convective zone. And that means that now if the plasma is subject to the differential rotation of the sun, it's going to be dragged around in the equator and wrapped around the sun,
mhm.
in the interior of the sun, round and round and round and round and round. And as it's being wrapped around, it's taking the energy of the differential rotation and it's transferring it, it's building it into the tension of the magnetic field. So the magnetic field is acting like it's a weird thing where the magnetic field acts like a, a string, right? It
Yeah, yeah, yeah,
acts,
exactly.
we have a pressure associated with magnetic fields, and because of the fluid nature, we're dragging the magnetic field around, we're churning it around, we're making more magnetic field. So we're building up, and these are drawn in this diagram here, these wreaths of magnetic
Hmm.
field in the north and the south hemisphere. And you can see this one here that's in the very equator is the bit that we're like pulling around, let's say, to twist it around. And at some point, we make such strong magnetic fields at the very bottom of the convection zone, that the magnetic field, similar to how it suppressed the convection at the surface of the sun to make sunspots, it basically makes a pocket of material slightly less dense because it's providing a pressure. So we have the plasma pressure and we have the magnetic field pressure. And by generating more magnetic field, we've increased the magnetic field pressure, which has allowed the plasma pressure to drop. And so the density has dropped. And this bubble of plasma then bubbles up with the magnetic field attached to it. And that then comes through the surface. And because of in general, what we think is because of the Coriolis force, so the fact that the ball is spinning, the sun is spinning, like we generate a cyclone and a hurricane in each hemisphere of the Earth, the rising parcel of plasma and magnetic field gets a bit of a twist, and it comes through the surface, and it's going to have a field line, a magnetic field line that basically goes in the opposite direction to the one that we started off with, the big one. And that magnetic field is then going to cancel the existing magnetic field on the sun. It's going to be dragged around to the poles of the sun, and then we're going to end up with a new magnetic field, a new dipole magnetic field that we can start the process with again. And actually, what I can show you, if I go back to one of the start slides, here we go. If I go to this slide, so here I'm showing you a longer time series on the bottom here of sunspot number. So if we just look at the black line, this is our solar cycle that I was showing before, tick, 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 and this is like the cycle that we're currently in. In the top panel, what I've done is I've taken those maps of the magnetic field. So maybe I'll show you one very quickly so you remember. So I've taken the maps of magnetic field that look like this. And what I've done is I've averaged them all longitudes onto a single profile in latitude. Okay, so I'm going to average all the magnetic field along this way to get the average magnetic field at the pole, the average magnetic field at 60 degrees, all the way down. And then what we've done is we've stacked that information on top of itself over and over and over again. And so what do we see? We see two main things. One, when we're at our minimum of activity, so that's when we have our nice dipole picture of the sun's magnetic field, the average magnetic field is looking like a dipole. So it has like a blue in one hemisphere, red in the other hemisphere. Then as the spots or magnetic features appear on the sun, we get more and more sunspot number. We can see they appear at around 30 degrees, and they are advected. They're dragged around the surface, and they essentially cancel out the polarity of the polar magnetic fields until the poles, which is what's happening right now, actually. The poles of the sun right now are very void of magnetic field. And then this process continues, we're still in this trend of building up this polarity of magnetic field. So we're letting all of the magnetic field that we generated inside the sun bubble up, bubble up, bubble up, bubble up. It's reinforcing the opposite polarity. So it builds and it builds and it builds until all of that flux has been removed or it's finished bubbling up. And we now have a new dipole, but now it's the opposite way directed. And then we start the process all over again. And this is a very famous solar physics diagram. It's called a solar butterfly diagram because it looks like butterfly wings. And so we have this process that repeats over and over again along with the solar cycle. And the interesting thing about that is even though the sun's, the hemispheres of the sun look like they're doing very similar things, they can often be slightly desynchronized. So for example, the southern hemisphere cancelled its magnetic field much later than the northern hemisphere of this cycle, of the last solar cycle. And that is one of the reasons why we have this double peak structure. It's not always the reason, but it's one of the reasons we get this double peak structure in the sunspot cycle. So that's I would say it's a very rushed and quick way of explaining the solar cycle. But
a lot of stuff, but it's very fascinating.
It's very complicated. And the other thing to mention is if people are wanting to do a career in astrophysics, we still don't understand the sun's solar cycle. And the added bonus of this is it takes 11 years for your theory to be disproven. So you can do a PhD and a career in research before your theory on the solar cycle gets debunked.
But the parallel that kind of always comes back to me, of course, is that the Earth is it's different in many ways, but the Earth, of course, flips its magnetic field every so often in a similar cycle. There's a lot of again, there's Coriolis, Dynamo, and stuff happening in the Earth's core. Slightly different
Yeah,
physics there, but at least taking a long look, this is kind of what we have to look forward to, and maybe thousands of years. We'll go from, because the Earth's magnetic poles will look kind of at the moment like the figure at the top right, but eventually we're going to have this crazy business of magnetic fields, all over the place. North will flip to south, and I think there's a lot
yeah,
to
and
learn between these two kind of.
yeah, it's very interesting because, well, essentially it, there's a lot of similarities, but there's also a lot of
Yeah.
differences.
Hmm.
In terms of the actual the physical mechanisms that are going on. But one of the core things that is true is that you have a conversion of energies, and in general, this is the thing that is tying those two things together. You have magnetic energy in the field, and you have a kind of kinetic energy or a rotational energy in the plasma that's generating the dynamo, that's generating the magnetic field. And so it's just about the interplay of timescales of like how long does it take for you to transfer one form of energy into the other one. And because the Earth's magnetic field is being generated by molten iron, the timescales for that changing are a lot longer. Which seems weird because we're such a small object compared to the sun. But for the sun, it's just plasma, and so plasma does what plasma wants to do, and the timescales allow for it to have such drastic changes. Um, and we see this, we even see on other stars, we see cycles of activity that are even shorter. So some stars can have cycles that are like 2 years. So every 2 years, it will go through a peak of activity, a quiet, peak of activity, quiet. Um, so yeah, and just in general, like for people who study dynamos in general, there's a lot of similar physics basically.
Yeah, yeah, it's very interesting. Yeah.
And I guess I can wrap this kind of section up
Hmm.
by just saying that, so if we think about this diagram kind of implies that we have at one point we have the sun's dipole, so the dipolar component of the sun's magnetic field is aligned with the rotation axis in one direction, and then 11 years later it's aligned in the other direction. And so it means that if we, there might be we break the sun's magnetic field down into different multipole configurations of magnetic fields. So you have like a quadrupole, an octopole, like basically how many closed field loops you have in a structure. You have similar kind of things in physics when you talk about like waves on a sphere and different things like
Yeah.
this, or quantum energy levels and
It's
things like this,
basically
and wave functions.
the hydrogen atoms, various angular momentum. Yeah, okay. If you've seen.
Yeah, and so basically we can take, for example, let's say, let me go back to our example magnetograms. So with the when we're at minimum, it's very easy to say like, oh, if I extract the simplest the dipole configuration, where should be the global north and where should be the global south, it's very easy to do. Here we can get basically we can do a deconvolution into spherical harmonics, what we'd say, and we extract from that like the location of the dipole that is underneath all of the complicated field. So what we can do is essentially we can plot a diagram that shows how the sun's dipole is flipping over with respect to the solar cycle. And so if I show you this here, I've added the last two cycles in for comparison, but we can just look at the black line, which is our current solar cycle. So here I'm showing the latitude of the dipole. So if we imagine just using our arm to give the orientation axis of the dipole with respect to the rotation axis. And then along the x-axis, we've got time. And so you can see we're roughly where the red arrow is. So in 2024, we've just crossed over. So the dipole's just flipped over and is just heading into the other hemisphere. And we can see from cycle to cycle, in general, the dipole flips over very quickly in about 3 years. And then the rest of the cycle, the rest of the 11 years, is just it getting back to being fully aligned again. So the blue is, the last solar cycle, which I said was very asymmetric. The orange is the cycle before that was very strong, but in general, they're all kind of following the same kind of trends, right? And I can add in some models to give you a sense of what's happening. So we've got the red and the blue, then we've got red and blue, but it's more complicated. Red and blue, but it's really tipped over now. Blue and red, blue and red, blue and red. Okay. The interesting thing to connect it with our discussion from earlier is that we can see. Wait, let me go. Let me just skip past all this. Where is it? Let me go to here. So if I look at this diagram, it's not a smooth transition of the dipole falling over. So if we think about the Earth's magnetic field reversing, for example, would be a similar kind of transition. There are these kind of like plateaus where we have a smooth transition and then it stops at a given latitude, and then we have a smooth transition and it stops. And I've tried to highlight a couple of them. We've had quite a few during this last solar cycle. And it turns out that these times when there's essentially the dipole part of the sun is like stopping, tipping over, is when we have these large hotspots of activity forming. So if you remember, we had this, I'll show this one, this hotspot that was appearing in this area. If I now show you what the magnetic field of the sun was looking like during 2022 when it emerged. So it's going to emerge in this region here, and you can see it bubbling away, bubbling away, bubbling away, bubbling away. Essentially, because there's very strong magnetic fields in this region, it basically kind of held the sun's dipole component in a given configuration. So this black line that I've got in all of the models shows basically the transition from positive to negative polarity in the model. Okay, so if you imagine we have a place on the surface that is very strong with positive and negative, it means that the black line has to go through this region. And so that means that if the dipole, like the red and blue transition, is trying to move through that region, it essentially gets stuck because it can't actually pull itself out of these strong polarities. So it has to wait for those to decay. And once they've decayed, then it can continue to rotate. And then maybe another region bubbles up and it stays and it becomes a very persistent active region and a hotspot, and that gets stuck again. And so actually, if you look back in the long time history of like the sunspot cycle, we see these kind of these stalling events quite commonly. Actually, you can see them like I showed in that diagram, or I can show you another diagram that's like this, where I've got sunspot cycle on the top, and I've got the dipole tipping over and then tipping back over in the bottom one, and you can see very clearly these shelves that appear in the dipole. And in general, they are due to these these very concentrated active regions that form for long periods of time.
And so this is also along this sort of, this weird axis that, is that right? Or are they anyway?
Exactly. Yeah, precisely. It's the same thing.
Yeah. So there's some weird axis that has preferentially magnetic field emerging along, and it sort of seems to pin and stall the flipping of the whole dipole structure. Okay, very
exactly.
Yeah.
So this is stuff that I'm working on this year. So this is it's even like a little bit new for me, right? But I got very interested in this, and it is something that people have researched. Actually, well, there's a funny thing people say in solar physics. Some research topics in solar physics become popular every 11 years.
Yeah.
Right? So if you imagine right now, this is a great time to study this.
Right. Yeah.
But if I was a PhD student in if I'm doing research in 2020 and 2019, I'm not really going to be interested in this topic. So it's waxing and waning interest. but yeah, so I'll keep you updated in how that goes. But in general, yeah, we're finding those kind of these hotspots can be quite important. So they're quite important for the structure of the sun's magnetic field, and they're quite important for how many X-ray flares that we get. Um, so, and with the combined observations we can do with the modern spacecraft, we can kind of get a better statistical point of view on them. But yeah, um, I don't know if are there any questions? I
Not
don't know
so
how
far.
long you want to, how much longer
Yeah,
you want to go for.
we can. I mean, it's up to you, but we can certainly go for another 15 minutes at least. Um,
Okay, I can give you the last. I can give you the last topic.
yeah. Okay. Let's do that.
Um, yeah, and that's to do with. Let's think about. So we have this nice picture for the internal rotation profile of the sun. So we know the equator of the sun is rotating faster than the poles. The question I now have is, okay, let's say I'm more interested in the atmosphere, in the corona, and in the wind that's coming off the sun. What is the rotation rate of the atmosphere above it? Okay, and so here I'm showing again something we've already seen, a bit of a comparison between what the sun's atmosphere looks like during low activity and during high activity. So here we have the sun in the middle. Um, the first line is marking the photosphere, like the lowest the start of the atmosphere, and then we have the coronagraph images, which are based on the scattering of white light when we block out the sun. So we can see our nice dipole that we have at low activity, and then we can see at high activity much more complicated, small like structures that are changing where the solar wind is coming out of. So if we think of the solar wind or the atmosphere that's flowing away from the sun, at solar minimum, most of that is coming from the poles. We can see it sculpting out this area here. At solar maximum, we have a lot more wind that's coming from different latitudes. So we have the role of the magnetic field that's emerging, essentially creating more channels for it to come out. So now, if we want to extend this diagram, how might we go about that? Well, I'll go back to this diagram we had for the butterfly diagram, which we've already nicely explained. So here's the evolution of the sun's magnetic field in time. And we see our lovely polar field reversals in the butterfly diagram that we have, the emergence of spots. What we can do is we can say, okay, let's take our magnetic field maps and let's do a model like this, a very simple model, where we just extrapolate where the magnetic field lines need to go in the atmosphere. So at solar minimum, we have something that's like this, and at solar maximum, we have something like this. And the magnetic field in this we consider to be basically potential. So it's basically you solve one of this like a simple Laplace equation. So it's an equation that basically you give a we say we have a magnetic field at the photosphere of the sun, and at the outer boundary of the model, we just want the magnetic field to be open into the solar wind so that it can escape. And we need the inside this bubble that we don't have any strong kinks in the magnetic field or any divergence of the magnetic field. And that basically provides us with a simple extrapolation technique. The point here is that we do this extrapolation, and then what we say is, okay, for all of the field lines that interact with the outer boundary, let's look for at where they come from. Okay, so if we take our solar minimum model, obviously, as I've just said, we have these loops around the equator. So all of the solar wind is going to be coming out of the poles. And so in this top diagram, I'm showing you a histogram of where the wind is coming from. And if we look at our solar minimum, which is when we have our nice like blue, red or red blue color with no spots in the middle, we can see that quite clearly in the histogram, the opening from the poles into the wind. As we move towards more active times, we can see that the emergence of sunspots and these magnetic field concentrations allows for more wind to come from nearer the equator. Okay, and as I've said previously, we know that the equator moves faster than the poles, so we could make a very simple estimate already right now, just looking at this diagram. If I add a color map to this top diagram, Now, whenever something connects to the faster rotating equator, I color it red, and whenever something connects to the slower rotating poles, I color it blue. And we can already get a sense of if we're modeling the rotation of the sun's atmosphere, what should happen as a function of solar cycle. We can see that at solar minimum, we're going to have a slowly rotating uh, magnetic field because it's all going to be anchored in the slow rotating poles. And at the maximum of activity, it's all going to be anchored into the equator, and so it's all going to be rotating around much quicker. Okay, and so we get this evolution of the rotation of the sun's magnetic field as a function of solar cycle. And we can go back to our diagram that we had before, and we could say, okay, what's kind of the average picture that we might have for filling in the gap, in the white gap of the rotation rate that we see in the corona and the solar wind. And if we take the models that we've just made and we do a naive kind of like averaging bridge in longitude, we get this kind of picture. So basically, we have our slow polar fields, which are dominating the solar wind, and we have some magnetic field that comes around on the closed magnetic field, but not very much. And then at high activity, we're not seeing these these structures just because of the averaging that I've done in terms of longitude. But in general, we see that the faster rotating plasma in the photosphere is dragging more of the coronal magnetic field. And we have a bigger impact in terms of the rotation. So we have a much faster general average rotation. Yeah, and I think that's where I'm going to leave that one. So I can put this diagram up as well. So we have what we've talked about so far is using Earth and solar orbiter to look at the sun, which is where I had the sun for the introduction slide. But now we're talking about how the internal rotation is influencing the rotation of the corona, and how that's influencing the rotation of the solar wind. And this rotation of the plasma is also, if I double back an hour ago, was what we were talking about when I was talking about sun-like stars have their rotation periods evolving in time. And so the faster you can spin your coronal plasma, so the more often it's connected to the equator, the more angular momentum the sun can throw away, and so spin itself down quicker. And so it's everything I've talked about throughout this whole process has been completely all coupled together and connected.
Yeah.
Yeah.
So,
I don't know if
no, that's very interesting. Yeah. Lots to think about. But so yeah, I guess the most interesting thing to me was this idea that we can get to such a low amount of solar activity that we can lose solar activity altogether, and that we could see that in extra, other stars as well. It's very interesting.
Yeah, actually, I should have put a diagram. Someone made a really beautiful diagram for a review paper recently where they just put like 3 sun-like stars. So from this sample of like 100 stars we have, one that's slightly more active than the sun. So it has its cycle period is like I think it's 7 or 8 years instead of 11. So it's oscillating more than the sun. And then another a star that's older than the sun, but very similar, and its activity profile is completely flat. Over the last few solar cycles, its activity is just flat. So you have this beautiful figure that's just showing this transition that we think is happening in stars.
A little bit like ECG or something, or heart rate
Yeah.
of beep beep beep.
Yeah, exactly.
And the other one's flatlined. Yeah. Okay. Right.
Yeah, and actually, so one interesting side effect from that, which I'm unsure what the effect of it would be, is that, so if we think about so let's imagine that solar activity does completely decrease. One of the main things that the sun's activity does do in a positive sense for us, rather than just attacking us all the time, is solar activity essentially flings sun's plasma into the solar system, and the plasma that it puts in the solar system acts as a barrier for galactic cosmic rays, so things that are very energetic particles that come into the solar system, and it basically acts to either, scatter them or deflect them or absorb them and things like this. So if you have a more quiet sun, what it means is you have more of these galactic cosmic rays that come into the solar system. And this is really quite bad actually for example, astronauts or airline pilots and crew and things like this, because those are the particles actually that are the most extreme end of the energy spectrum. And you really don't want to get like a big dose of radiation from these, because these are like really going to give you like cancer or things like this. And so you can imagine in a case where we do have a sun that's very quiet, actually, radiation levels in space go up actually quite badly. And like the broad distribution goes down, but the tail end comes up. And so I haven't thought about it too much, how much that would actually, if that's worse, better or worse.
Yeah, no, that's again something interesting. We better get to Mars. I mean, this is going to happen over very long time scales, but again, something implications for life elsewhere, implications for the Fermi paradox. I think a lot of people watching this are interested in, why aren't we seeing aliens? What are the chances of having intelligent life? Maybe they get adversely affected if their star flatlines. Maybe they get adversely affected if their star is too chirpy and
maybe it's very, very hard to leave your heliosphere, your bubble of protected plasma, because the interstellar medium is very harsh, and we just haven't really accounted for that yet. Yeah.
So again, just shows us, maybe there are some kind of implications for the sun being quite special and unusual in that respect. Yeah, interesting. Okay, I mean, is that you happy to end there? Shall we sort of?
Yeah, I think I did manage to get through most of my material actually, so that was quite good. And yeah, I hope it's all at least been even though it might have come in a different order. I hope it's been kind of, we were able to together tie the pieces together for the audience so that they got the whole picture.
Yeah, so I certainly learned a lot. Some takeaways, firstly, lots of different scales, lots of different weird things happening. This sort of almost like butter churn or churning up of magnetic fields, this bubbling up, plowing up a magnetic field out of the sun. Very interesting. This strange sort of axis that's present there that I wasn't aware that there's some, not quite the north-south axis sticking through the sun, the sort of pin through it that is causing strange activity. As we said, maybe someone like Elon Musk should invest in at least a sort of guardian satellite that's going to watch, one of the sides of the sun relative to Mars, or relative to a Mars transfer orbit, to kind of watch out, be a sort of sentinel for any sort of eruptions or flares that might happen. Yeah, lots of interesting stuff, I think. I think again, there's a lot of this methodology can be applied and should be probably applied more widely to Earth-based fusion for sure. Yeah, very interesting. Well, yeah, so it's been a real pleasure having you on. So thanks for coming on.
No, it's a pleasure to come on.
Yeah, and I definitely
lovely to have a discussion. It's slightly later for me than you, but it was still pleasure.
Well, thanks for staying up quite so late. Definitely, I want to have other interesting guests on in future. Hopefully, we'll all learn something. We certainly learned some, and this was a good first kind of guest live stream on this channel for sure. I hope the viewers now and the ones that come back to this also enjoyed it. Yeah, so with that, I'll say thank you to Adam. Thank you to the viewers for watching. I will see you all in the next video.